The last speaker of the morning is Professor Andrea Isella. He's from the Department of Physics and Astronomy at Rice University, and he's going to be talking about the origin of habitable planets. He's the last speaker, so while he's getting ready, I just want to mention I'm really impressed by the variety of the talks this morning across the board and the different issues related to this space travel.
Okay, thank you very much and good morning. We're going to shift a little bit gear here. So this morning we have heard a lot about application and about how we build habitable environment in space, right? So we need architecture to build habitable environment on the moon. We need to shield and glasses to protect ourselves. And this is one part of the story, is a very important part, and is a fundamental part if you want to, explore the solar system with humans. The other part of the story, and that's where I come into the picture here, is we can go and try to search for habitable environment, meaning that Earth is obviously a nice habitable environment, and we have been searching for habitable environment in the solar system for a very long time, and searching for habitable environment is really one of the motivations for which we send probes to Mars, right? To see if there are at least resources that will allow us to live there or on the moon. And, in the solar system, there are not many habitable environments. Actually, the only habitable environment we know about is the Earth. And despite the fact we have been searching for habitable environment, see if this comes, there is a little, okay, here it goes. We have been exploring Mars for a long time with rovers, and we are looking for sign of life, or at least past life. If we find sign of life on Mars, past life, it at least tells us that at least in the past, Mars was an habitable environment. And so Mars obviously is the first target because Venus, we know, is pretty nasty environment, so we are not going to go really there to look for life. Mars has a tenuous atmosphere, is a bit too cold, is a bit too small, and that's why today, for example, we don't have liquid water on the surface. And if you look beyond Mars, within the solar system, the other place that is perhaps the best example or might be a life-supporting environment are the moon of Jupiter, and particularly Europa. And so NASA, for example, there has been a lot of work done to send probes to Europa. This is a picture of the Clipper mission that will probably launch at the end of next year. And Europa is this big moon which is covered by ice. The idea is that below the ice there is an ocean, maybe of liquid water, and we know for sure that there is water. We see water plumes coming up from Europa. And so the idea is that the probe will gonna search and scan the surface, try to find chemical evidence of life on Europa. But the key point here is that in the solar system, there are very few habitable environments. So Earth, again, is the only one we really know. And so that raises a lot of questions, right? So why are life-supporting environments so rare in the solar system? Is there anything special with our own planet? How did Earth form? And is Earth the only type of habitable planet out there in the universe? How rare is Earth? I mean, there are gazillions of stars in the universe, and I'm gonna go back, touch a little bit about that. Pretty much every star in the universe has planets like the solar system, but we really don't know how rare is having a planet like Earth. And then you go to the very big question. So is life possible elsewhere in the universe? This morning we have talked about exporting our lives somewhere else in the solar system. Obviously we cannot go very far because our propulsion techniques are still limited. That's the speed we can achieve are only, it takes forever already to reach Mars and planets beyond Mars, let alone nearby stars. So this is more like a theoretical question whether life is possible elsewhere in the universe. And so what does it take to build and preserve an habitable planet? So I'm an astronomer, so I use telescope, I look up at the sky, and the question I'm trying to answer with my tools is how you build planets like Earth, how common these planets are in the universe. And if you think carefully, if you ask yourself, okay, what does it take to have a planet like Earth? So what do we need to have a habitable environment? And, you know, as we talked this morning, we need to have something that shields us from the right temperature, right? So it doesn't need to, it cannot be too cold or too hot. For a planet, it means that, for example, you want to have water in a liquid phase, you want to have oceans. If all the water is frozen, it's not very useful. Or if all the water boils up in the atmosphere, it's not very useful. Chemistry is very important. You want to have a planet with the right amount of life essential elements. We are made of carbon, so you want to have enough carbon. We breathe oxygen, nitrogen, and all the other elements that are very important, obviously water. Water is actually a pretty difficult, so most of the water on Earth did not form on Earth. Most of the water on Earth comes from space, either during the formation itself of Earth or was delivered to Earth during the lifetime of Earth. The planet, for example, cannot be too small, otherwise you end up having like something Mars that cannot retain its own atmosphere, but you don't want the planet to be too big either, because then you have too much pressure and the chemistry is different, and then maybe life is not going to be able to survive. And then many other things that we really don't know. For example, Earth has a magnetic field that shields us from both solar and interstellar radiation, and protects our fragile cell and fragile DNA from cosmic rays and solar particles. So we don't know if having a magnetic field like Earth is really key to have life, right? So for example, Mars does not have a magnetic field, and we think that Mars lost its atmosphere, in part because it's small, and in part because not having this shield led the solar radiation to strip away the atmosphere of Mars. And then, for example, you also want the planet to be around a star, which in our case is the sun, that is quiet, right? It doesn't sneeze or doesn't have too much what we call solar flares or coronal mass ejection that can strongly impact our life activity. NASA spent a lot of money to monitor the sun in what is called the space weather, because if you have a solar storm coming toward us, that has very strong impact of all our technology. And so, for example, the astronauts in the space station, if there is a solar storm, they have to take shelter, and also our electric grid really is very affected by solar activity. Okay, so all these questions are clearly driven by the solar system, but in the last 20 years, there has been a revolution in astronomy, because until, say, 20, 30 years ago, the solar system was the only known planetary system. And so, everything was about us. But nowadays, we know, thanks to astronomical observation, that pretty much every star in the universe has a planetary system, in average. And this figure shows, we have discovered thousands of exoplanets outside the solar system. And each dot is one of these exoplanets. Here is the distance from the star. So the Earth is at 1 astronomical unit. Some planets are much farther away than Earth. Some planets are much closer in. And on the y-axis is on the vertical direction is the mass. And the only reason I want to show this, not because you really get the number, but to show you that the planets that we have discovered so far are very, very different from the planets in the solar system. As you can see, for example, there are no blue dots at the position of Earth, no blue dots. And we don't see planets here, not because they don't exist, but because they are very hard to detect, right? So our observation preferably detect planet in the top left. So we found all these solar systems outside the sun, but they are very different from our own, right? And so that also, brings the question of, are we unique in the universe? Is life on Earth unique? And to even reinforce this point, in the last 10 years, we have discovered that perhaps the most common type of planets in the universe are planets which are these two gray beams here, which have radii between 1 and 3 times the Earth, so bigger than Earth, and are something like between Earth-like planet and our gas giant like Neptune and Uranus. And we don't have any of these in the solar system. So at least it looks like the solar system is relatively weird compared to all the other planetary systems. So how do you go about trying to solve this question? So what does it take to build an habitable planet? Is life common in the universe or not? We can study the solar system in great detail. We can send probes and we can send astronauts on the moon, on Mars. and everywhere. And that's perfectly fine. But there are two main problems. One, the solar system is unique, right? So it's like you do experiment once, and then you cannot repeat the experiment, so that doesn't give you very robust results. And the other problem is that the solar system is old. And I don't want you to go through this, but the point is that the solar system is about 4.5 billion years old. And, but the condition for life, Earth, formed in the first 10 to 100 million years. And then there have been a lot of time where things happen in the solar system. We don't know exactly what happened. And so we don't know if, and we know that life actually on Earth developed, the first form of life developed very, very early on, and after the formation of Earth. And so the point is that the solar system is a very limited laboratory. And so astronomy gives us a tool to complement what we can gather by just exploring the solar system. And this tool is, we have this special kind of time machine that allows us to observe today how planetary systems are formed. So, as I said, I'm an observational astronomer, so I use telescope. This is a beautiful image of, if any of you is an amateur astronomer, you probably know this one. This is the Orion Nebula, an image taken with the Hubble Space Telescope. And what you see here is a region where stars are forming and planets are forming around new stars. And planets are teeny tiny and stars are teeny tiny, so these scale are huge, right? So these scale are much, much bigger than the solar system. But thanks to the new technology, we can zoom in and trying to find baby planetary system. And when you zoom in this region, you find objects like this one. This is one of the many, actually. What you see here, essentially, is a planetary system information. So I have a very professional comparison. Here you go. So that's your baby, right? So what you see here is a planetary system information. There is a newborn star at the center, which is that white dot. And surrounding this newborn star, you have material that, through processes that we don't understand, and that's why what my research is about, this material come together and form planets. And sometimes it forms planets like Earth, which are very nice, and sometimes it forms planets like Venus, which has very toxic atmosphere, or like Jupiter, which doesn't probably even have a surface. And so we want to understand the processes that lead to the formation of planets, to understand how rare or how common is the formation of an habitable planet. Okay, so if you want to see this baby planet, this picture is still not very satisfying because these are huge scale again. So now you need a even more powerful telescope, and you want to zoom in even farther. And that's where there's been a lot of technological development in the last 30 years. So you are all very applied. You do a lot of applied research and applied science. I'm much more fundamental research. But at the end of, in a couple of few minutes, I'm going to show you that there are actually strong technological application and a lot of motivation to develop new technology when you want to study this kind of object. So these are two of the telescopes I use mostly. They are very different. They are both in South America. You have to put telescope high up in the mountains so that the atmosphere does not interfere too much. The Hubble Space Telescope in space, and I have an image later of the James Webb Space Telescope. And they are very different. On the left is an optical telescope. On the right is a radio telescope, which is a collection of big antenna. Each antenna is 12 meters in diameter. You can see here a pickup truck, just in comparison, which is teeny tiny. So each of these antennas is a 3-story building, and there are 64 of them. And you need big telescope to observe very small objects. So these baby planetary systems are very small in the sky. They are 2,000 times smaller than the full moon. And you need a big camera, essentially, to resolve them in great detail. But so in the last 10 years, this telescope came around, particularly the radio telescope on the right, around 2011. And so they gave us a lot of room to improve our imaging capabilities. So this is one of the many objects I observe. On the left is an optical image. You have these baby stars that are, when they are formed, they are really surrounded by a lot of gas and dust that is falling into the star and creating these, what we call a circumstellar disk, that is the progenitor of planets. And then you take the radio telescope I had in the previous picture, you point toward the center, and what you can do now, you can have a much more clear image of the innermost part of the system where planets are forming. And these images are, imagine you have a time machine and you go back 4.5 billion years. This is what the solar system might have looked like when the Earth was forming out of this material. So I'm not going to go in any details about how we actually analyze these images, but we can do imaging in multiple wavelengths. We can do spectroscopy, molecular spectroscopy, atomic spectroscopy. We can measure the molecular composition, for example. We can measure how much water you have, how much carbon you have, how much oxygen you have at different distances from the star. And now if you can measure how much water you have at different distances, and you know, you can see where the planets are forming, you can tell whether a planet might be formed, for example, with a lot of water or very little water, with a lot of oxygen or very little oxygen. And so we measure things, for example, ratio between carbon and oxygen as a function of distance, and we try from there to infer what kind of planetary system we have. This is another object, is a famous one, it's called TW Hydra in the Hydra constellation. And just to put it on the scale of the solar system, if you put the solar system on top, this object that you see is really the scale of the solar system. So let me explain a second what you're actually looking at here. So there is a star that is forming at the very center, and when you look in the radio, this star is invisible actually, which is actually good. And what these orange stuff around, this is dust. These are like sand particles, like grain of sand, with sizes of the order of a fraction of millimeter or millimeter, that are orbiting around the star, right? And the planet form by aggregating these particles. So you start with micron-sized particles, they come together, they stick together, they grow and grow and grow, and eventually you have planet like Earth. On top of that, you need to create water, you need oxygen, you need other objects, other elements in order to have life, right? So in the last 10 years here at RISE and with colleagues, we did a lot of this kind of observation. We are collecting many, many objects. Each of these one is a baby planetary system. We have hundreds of them. And using statistics now, we are trying to gather information about how likely it is to form habitable planets. And this is really a tricky problem because, well, first of all, we cannot build a lab here on Earth where we can actually build planets, obviously. And it's also a tricky problem because it connects, there are many physical processes involved. So as I said, your building block for planets like Earth, so your initial material, are these micron-sized particles with a size of 1/1,000,000th of a meter, right? But you want to get something like Earth, which has size of 6,000 kilometers. So there are many orders of magnitude involved, and there are many different processes involved. And the only way to actually see these processes is by looking with telescope at different wavelength, different tracer, and try to build up all this sequence where you go from small particle and they collide, they grow in size. Eventually you reach objects like pebbles or centimeter objects, and then there are a lot of things we don't understand because if you try to smash pebbles together, they don't stick very well. They tend to bounce, fragment. And so there are things like bouncing barriers, fragmentation barriers, that we're trying to figure out how nature overcomes those by looking at this observation. Eventually you have objects like Mars or like the dwarf planets in the solar system like Pluto, like Ceres, and they are big enough at the point, what we call planetesimals. They are big enough that they can attract other objects and grow farther in something like Earth. And if there is a lot of gas around, then you create a lot of atmosphere and you may have, for example, giant planets. So there are many, many complications in the formation of planets that we are trying to understand through this observation. And really only in the last 10 years we have the technology that allow us to solve some of these questions. Sometimes we see even, this is something I did a few years ago. So we observed this baby planetary system, we see a planet there, and we see a disk around the planet. So there is a planet that is forming, there is a disk, and this disk is probably when the moon of the planet formed, like the moon of Jupiter, forming a disk around Jupiter. And this is something that really captured, I put that one up there, so there was an article on the CNN about this article, not because I want to really show that we went on CNN, but because this is really something that captured the imagination of people, right, and the media. And it's very good for science because obviously it brings money. Sometimes we have to convince people why you need to spend billions of dollars to take a picture of something that is so far away and does not have a direct connection to our human life. It's not better to spend billions of dollars to cure cancer. And obviously the answer is yes, but there are a lot of applications, and in the last few minutes I would like to show you what we can do. What are some of the applications of this technology? So, obviously the questions are mostly fundamental research, but that triggers a lot of technology development and innovations. You are the wrong audience, obviously, to preach about this because you all work in the space sector. For example, the James Webb Space Telescope that NASA launched a couple of years ago now provides these beautiful images of this planetary, what is called star-forming region that you might have seen in the news. So this is a telescope that is in space at Lagrangian point. And if you want to see what kind of spin-off the building of the James Webb Telescope had in terms of medical devices for medical imaging, new materials, I put the link over there. It's a pretty old link, so NASA didn't update that recently. But just to show you some of the spin-off that when you try to answer this very challenging question, you need to build. So when people start to think about JWST, there was no technology. So all the technology in JWST essentially was built on purpose. And then that has a lot of spin-off in other activities. So I want to finish with just mentioning two projects that we are heavily involved here at RISE. One is building a new telescope, a new radio telescope. It's called the Next Generation Very Large Array. Maybe some of you know about the Very Large Array in New Mexico. It's a radio telescope up in the mountain in New Mexico. It was featured also in movies like Contact with Jodie Foster. And we want really to expand this telescope to be able to image the formation of this planetary system and other things. This is a very large program that as all the United States is involved and also international partner. Every 10 years, the astronomical community gather together and decide the priority for the next 10 years, what is called the Decadal Survey. The last one was in 2020, and this project was a top priority, and so now is under consideration by NSF. And here at RISE, we did a lot of simulation to optimize the design of the telescope in terms of number of antenna, wavelength, distribution, to really image the formation of this planetary system. If this is a movie of a simulated observation that one of my postdocs did a few years ago, where essentially we say, okay, imagine we have a baby planetary system out there. What will we see with this telescope? Or what do we need to be able really to pinpoint the formation of planetary system? And unfortunately, it's very slow, but what you see here is, so the bright spot there is a baby Jupiter, and Earth is somewhere in the center, and they are forming, and with this telescope, we can take picture and see them in great details, and we can also follow the orbital evolution. And then the very last is a smaller project that I'm involved. So together with other universities like Caltech, Arizona State University, the Jet Propulsion Laboratory, New Jersey Institute of Technology, we are building another radio telescope. It's made of, so there are these big antennas on the background, so don't look at those. So it's made of dipoles, these poles, 350 dipoles, spread around. This is located in California, in Owens Valley. And essentially, what you do with this telescope, you image the entire sky at very low radio frequency, as low as you can go from Earth, for those of you that have a technical background, between something like 15 and 18 megahertz. So it's very close to the radio frequency where you have your radio, FM radio station. And so what we do with this telescope, the main reason we are building this telescope goes back to try to understand the condition for life, and particularly something I mentioned before, meaning that if you have a planet around a star, it looks like the magnetic field is a crucial point for having an habitable planet because magnetic field shield the planet from stellar radiation. This is a very dramatic picture of what may happen if you have a very active star and a planet like Earth. When you have these solar flares, they engulf the planet, they can strip away the atmosphere of the planet if the planets are not shielded by magnetic fields. So what we are doing with this new telescope that is coming online right now is to actually monitor all this. I told you we discover many thousands of planetary systems. We can monitor the star to see if this star flares. And so try to understand what is the star doing, how quiet it is or how active. Not only that, we can also measure the magnetic field of planet, possibly, right? This is a very unique telescope, and there are no other telescope like that in the world. So we hope maybe in the next year or so to be able to have some great result about really trying to understand, for example, if all the exoplanets we see, whether or not they have a magnetic field. We have good candidates of planets that might be able to sustain life in the sense that they are not too hot and too cold, but we don't know anything about whether or not they have a magnetic field. Okay, so I'm gonna stop here. And so I hope to, so again, this was a bit different, right? Much less applied, but there are actually a lot of application in pushing this kind of, in trying to answer this question. So with that, I'll be happy to take any question.
We have plenty of time. So back here. Yeah.
Where is the Owens Valley complex? What's the advantage of that particular location? The size looking much nicer than Fort Irwin, which I have spent some time.
Where's the Owens Valley?
Oh, the Owens Valley.
Owens Valley and advantages versus, say, Fort Irwin.
So, well, I mean, this telescope is built in California for the reason that there was already a radio telescope. Owens Valley is in, between the Sierra Nevada and essentially the mountains you see up there is the Sierra Nevada, Yosemite, and so forth. On the other side is the Death Valley National Park. So you need a very dry place. You need a radio quiet place because there are a lot of, when you do radio observation, there are a lot of human interferences. And as you can see, there is not much in Owens Valley. I mean, the reason why we are building the telescope there, because there was already a facility, which is the Owens Valley Radio Observatory, where you have many other telescopes that you see on the background. There is a similar facility in New Mexico. You can build facilities like this in Texas. You can build, at this frequency, as long as you are away from a city like Houston and you don't have too much radio interference, you can build them pretty much anywhere. Does this answer your question?
Yeah, there are a lot of areas that meet the criteria you laid out. I was curious why, what's so special about this? I guess if you boil away the stuff that applies to hundreds of places, you get down to their existing facility.
Yes, originally, I mean, this facility as, this observatory probably exists since the 40s or the 50s. And so it's been used to host multiple kind of experiments.
More questions? One here? Yes.
Okay, to be clear, the habitable planets you're referring to would be for any type, I mean, even microbial life, or are you talking about specifically intelligent life for like people?
I mean, yeah, that's a very good question. I mean, when we talk about life, we generally talk about life as we know it, so life on Earth. I mean, it's everything. I mean, really, you start from microbes, right? It's more about, we call something habitable, again, going back to my list of requirements. If you have the right temperature condition, chemical condition, and so this is really the whether it can be supportive of life, right? as we know it. Whether then that life actually develops and to what point it develops is out of our range, right, for telescope. I mean, astronomy, there is a lot of search for intelligent life, particularly in the radio. You may have heard about the SETI program, where, using a radio telescope, astronomers scans the sky looking for intelligent signals, right, telecommunication, and things like that. That's a different story, but here is more about the chemical condition, the physical condition that can allow life to start. Yes?
Is one of the conditions the presence of a Jupiter? I've been told that Earth exists mostly because Jupiter takes a lot of the meteorite hits from outer space, and that without Jupiter, we would we'd be hit by meteors all the time.
Maybe, yeah, and perhaps many more. Jupiter can have that effect, and we are now learning that Jupiter might actually have a crucial effect in the formation itself of the Earth, because we know for sure that Jupiter formed before Earth, because Jupiter formed where there was a lot of gas around, and we think that the perturbation that Jupiter had on this material was a key point actually for forming Earth. So maybe Earth exists because there is Jupiter. This is one of the many things. The other is the moon, obviously. Earth is unique because it's the only planet in the solar system that has such a big moon relative to the planet. And the moon has a lot of effects for life. Tides. I think we think life was able to get out of the oceans because the tides helped. With tides, you have this region where it's wet and dry. And when the Earth was much younger, the moon was actually closer to Earth. And so the tides were even stronger. Maybe you need tides to have life. So there are so many conditions that we don't know. So there are the known unknowns. And that's why it's whenever you say, well, life can be very common in the universe, yes, maybe no. We really don't know.
Thank you very much for your talk. This kind of research has a strong potential of discovery. So considering the present technology and the evolution of technology, what is in your mind a possible time schedule for a discovery of important information regarding the new planets?
I mean, in astronomy, I think the time scale for discovery is really set by the time scale in which we can convince government to give us the money to build the telescope we need to do the research. JWST has been fantastic. Is fantastic. It just started, right? People are using JWST to now measure the chemical composition of these exoplanets we discover to see if in the atmosphere of these exoplanets you might have water, and even try to detect some biological signature. Right, which we still don't know what are the biological signature of life really well. So in the radio, for example, I was talking about this telescope NSF is considering, the problem is that it takes decades just to have enough money and enough support to start building this facility. So really, I mean, the time scale for discovery is really. Sometimes we don't have the technology, so it takes time to build the technology. Sometimes we have the technology and we are ready to go, but we don't have the fund to build this facility. So, and every time you have new discovery, I put the CNN article up there for the reason that the best thing to convince politicians that they have to give money is to show them that you have an article on CNN, because that somehow looks like the activation, switch, right? Because then they can go, in front of their constituents and say, well, see, I mean, this has an effect. So it's both. It's a little bit technology, but mostly money.
With that, I think we delivered on time, right? And the speakers did a fantastic job of keeping time. Thank you.